question of list decoding, we want to be able to retrieve the list of possible code words in an efficient way. So now I'm going to talk about the ABNNR Encoding. This is by Alon, Bucknell, and Roth. And they have a way to amplify the distance of an existing error correcting code in a very efficient way. So they take some error correcting code C, they applied the encoding to C, and they receive a new error correcting code C prime. And if C has some distance delta, that we think about delta here as some constant, but small constant, then this new error correcting code C prime has distance 1 minus epsilon, where epsilon is again some small constant. So the distance goes from small constant to nearly 1. And the encoding takes each code word in C into a new code word in C prime. So the number of code words stays the same and the rate will go down. And the decoding question here, so this algorithm has an efficient decoding algorithm. And this means that if C has a decoding algorithm from distance delta over 2, then C prime has decoding algorithm for distance which is approaching half. And what we want to do in this work is the list decoding question. That is, C, we still needed to just have a decoding algorithm from distance delta over 2. We do not require anything more from our base code C. But we want to list decode from distance which is approaching 1, approaching the distance of the error correcting code. So this is the goal of what we're doing in this work. So now I'm going to explain how the encoding works. So the encoding takes some x in C to y in C prime, and it uses a bipartite graph G that has, so if x is in 0, 1 to the n, then V0 here has n vertices. And the way it works is really simple. We just write each bit of x next to the vertices of V0. So every bit of x has, every vertex in V0 now has a bit. And then every vertex in V1 just looks at both of its neighbors, takes these bits, bunches them into a single letter. This is an important part. Now, 0, 1 here is not 2 bits. We treat it as like a single letter in an alphabet of size 4. And then this is going to be the encoding on location U. So if this is the entire encoding, then the first vertex takes 0, 1, and the second one takes 1, 0, and so on. So we lose here by the rate because we moved from n bits to some sigma, which is the degree of the vertices in V1, to the length of V1. But the number of code words stay the same because we just take each code word in X to a single code word in Y.
So this will have constant degree, this graph.
Yes, so this graph needs to have a constant degree, else we are going to lose the entire rate. Yes. So this is a constant degree graph. Are there any questions about the encoding itself? No, okay. So now I'm going to say how this amplifies the distance if the graph G is picked correctly.
Take it for a second to digest it, yeah?
Yes.
So the ratio between the size is the. So what happened to the rates really in this?
So if V1, so the rate goes down in 2 ways. One, because the alphabet goes down, it goes up from the degree of V. And if V1 is larger than V0, then it also goes down by the ratio between V0 and V1. So there are 2 factors here. Yeah, we lose in 2 ways in the rate. There is a different encoding in which instead of picking these 2, then the encoding is sort of these 2 bits. And then you only lose by the size of V1 and V0, and you don't lose in the alphabet size. But also then you're in a binary code and your distance is not approaching 1.
the expansion you need here is from the small side to the big size?
Yes, I'm going to the expansion is in the next slide. So how does the distance goes? So suppose we take two code words in C in the original aircraft encode. This means that they must differ on some set of coordinates in V0 of size delta. And if there is some vertex in V1 which has an edge in this set where they differ, then the encoding is going to be different on location W here. Because we bunch this, so then we'd see this vertex where they differ. So the property we need if we want to amplify the distance from delta to nearly 1 is that every delta size subset of V0 needs to have almost all of V1 as its set of neighbors. So this is not a very strong expansion property. It's like, first of all, it's not worst case. We only care about delta size subsets. And all we need is a size of sets of size delta or more here. Sorry. Sets of size delta or more are going to have many neighbors, like nearly all of V1. This definition is not a sampler. It's a weaker definition. And for distance amplification only, if this was all we wanted to do, this is enough. But if we want to do also decoding, only unique decoding, we need this graph to be a sampler. So now I'm going to say what is a sampler graph.
But so in the distance amplification, you change the size of the alphabet. It needs to be.
Yes. Yeah. In the entire talk, I'm always going to change the size of the alphabet. Yes. This is why a single neighbor is enough, because I take all the bits to a single array. Any more questions? Okay, so now I'm just going to define what's a sampler graph, regardless of the code. So it's a bipartite graph that for any function f which is defined on the vertices of V0, I'm going to speak about it not in a very parameterized way, but in this talk I'm not going to work on two parameters. So just assume that alpha and beta are really small constants. So for every function which is defined over the vertices of V0, almost all vertices U, if they average over F or on their neighbors, then this average is close to the total average of F. So
it is a function or it's a 0-1 function.
Yeah, F is a 0-1 function. This actually can be all the range between 0 and 1. It doesn't have to be 0-1. And what's important in this work is that if we have some set of coordinates V0, which is large respect to the sampler parameters, then almost all of the vertices in V1 has proportional fraction of their neighbors in V0. For example, if V0 here has size half, because it takes half of the vertices, then almost all of the vertices in V1 has half of their edges, here a single edge, because it's degree 2 graph, but has half of their edges falling to V0 prime. And this is actually the property that we're going to use in the decoding. So are there any questions about the definition here?
But maybe you can say that this is at least when
yeah.
V1 are roughly the same, then expansion is really equivalent to this definition.
And also, if you want to get this property from this definition, then you can do it by just taking F to be 1 on V0 prime and 0 everywhere else. And then if you average over the neighbors, this is exactly the fraction of your neighbors falling within V0 prime. So this is, you can get it from the standard definition. So now how do you decode? This is the standard decoding algorithm. So it's a unique decoding algorithm. So what's the decoding question? We receive some Z here, which is, these 0, 1 again are like a single letter. We receive some Z here that has an input for every vertex in V1. And we want to get some Y, which is an encoding of X. So we are looking for some X that when we apply the ABNNR encoding here, we would get something close to Z. So how do we do it? So we have each vertex here has a letter which actually means what X should be on its neighbors. So this U thinks that X should be 0 on the first one, on the first vertex, and 1 on the second. And this vertex thinks that this vertex should be actually 1 and not 0, and this should be 1. And this is going for every one of the vertices in V1. So every vertex in V1 has like an opinion of what X should be on its neighbor set. And if Z had no errors, 0 errors, then all these bits would be the same if it was really an encoding without errors. So this brings a very natural algorithm for decoding. We just do majority, like pointwise majority for every one of the vertices in V0. So for every vertex in V0, we just fix the value, which is the majority value for this coordinate. Then we get some string X prime. And hopefully, if everything was going well, this is really, really close to X. And we can apply the decoding and get X. And then apply E of G again and get the Y more. So why does this work? For this, we need a sampling property. So this is the. Okay, suppose we have some set of corrupted coordinates, and we want to say that this set, if it's less than half of the coordinate, can corrupt this X prime on more than delta over 2 fraction of the vertices. So if we want to corrupt a X prime on this set V0 prime, what we need to happen is that the majority of the outgoing edges from V0 prime is going to land inside the corrupted coordinates, because then the majority value would be non-correct. Okay, but because we have the sampler property, almost all vertices in V0 prime can only send delta fraction of their edges toward V0 prime. Sorry, almost all of the corrupted coordinates can only send delta fraction of their edges towards the V0 prime. So most of their edges are like wasted on places where there are not majority. So if we want to have a majority of the edges in V0 prime corrupted, then the fraction of corrupted coordinates has to approach half, to be nearly half. So this is why the sampling property is required here, then expansion is not strong enough to force this. So if we have the sampling properties, then the majority decoding works until about half of the coordinates are corrupted. But if half or more of the coordinates are corrupted, then it doesn't work anymore. Because if you corrupt half of the coordinates, then it might be that the majority is incorrect almost always. So still the distance is nearly 1. So we want to do something even if the majority failed. And like if we wanted to do decoding, we needed stronger properties than just to distance amplification. To do list decoding, in our algorithm, we needed to require stronger properties on the graph G than just G being a sampler, which was enough for the unique decoding. So if we wanted to reach distance which is approaching 1, we required stronger properties from this graph G. And what we required is that this G is going to be a part of a double sampler. So if G is a part of a double sampler, then we have an efficient list decoding algorithm which can list decode from distance which is approaching 1.
What exactly does that mean? Like, what is the number of codewords that will be in this board?
It would be like some order of 1 over epsilon.
Okay, so it's a constant number of words in the.
Yeah, it's a constant number of words. I mean, I think we can get 1 over epsilon. Well, we get 1 over epsilon squared if we don't have the base code C as a promise. And if we have this extra promise, then we can have fewer words, because we can check. Okay, so now I'm going to define what's a double sampler, which is just what we needed from the graph G to be able to list decode. So we need to add another layer. The encoding is done just before the graph between V0 and V1. These extra vertices, we need them only for the list decoding algorithm. They're not part of the encoding. And we needed this graph to be an inclusion graph. So in an inclusion graph, we have the set V0, we identify it with the set 1 to n, and then we identify every vertex with a subset over 1 to n. So like this S here is the set 1, 2, and 3, and edges go by inclusion. So if this is 1, 2, and 3, it connects to vertices 1, 2, and 3. And if a vertex here is a subset of the coordinates, it's connected to S, this means it contains S. So
It's if and only if between V2 and V1.
yes, in all cases, it's like you connect by inclusion. Like if you specify the sets, this is enough to specify the graph itself.
It's a simplified complex.
Well, only 3 layers, but
Yeah, okay, we can stop.
yeah.
No. The simplified complex, if you have a set, you have to have all the subsets.
You can think about it as taking a simplified complex and taking out parts of it. But yeah. So what are the sampling properties we needed? The first one is like a simple extension of V, the graph G being a sampler, which is just required that the graph between V1 and V2 should also be a sampler. And the second one is what we call the local sampling.
It
Yes.
says V0, V1, and both.
Sorry, so this should be V1, V2. Yes, so like this graph should be a sampler and this graph should be a sampler. Yes, sorry. And the second one is that we call local sampling, is that if we look for every vertex in V2, and then we look on the set of the graph that is contained in T, that is, these are sets which are subsets of T, and these are elements which are also in T. So this is a small graph. If it's a constant size graph, yes. It's a small constant size graph, and we wanted this constant size graph to be also a sampler. So this requirement is very strong because in fact, it's like linearly many constant size graph of the graph between V1 and V2. And each tiny piece of the graph should also by itself be a sampler.
Is this constant because you assume that the
Yeah,
second sampler is also constant?
yeah, like I assume that T, the size of the set T is constant.
Okay, which was not necessary because you said this is not a part of the code.
It's not a part of the code, it is not necessarily, but if you want to have our algorithm work efficiently, then this needs to be a constant. Yes. So any more questions about the definition?
Yeah, when you say that the small graph is a sampler, the error parameter is something like the distance of the code, it's very small.
The error parameters, so obviously you can't require it to be really strong one because the graph is constant and also the degrees are constant, but yeah, the error parameters should connect to the distance of the code that we want to get and to the distance of C, the base code. I mean, there is some relation here.
It will be a stronger, probably a stronger sample than the previous two because the degrees are not constant relative to the size. So it's,
The degrees are not,
it will
yeah.
be better, and maybe you need it also to be better.
I don't think we need it to be better, but yeah, it will be.
What degree will not be constant?
Well, I mean, a constant size graph, everything is constant, including
Like
the degree,
the
but the
degree,
degree can be square root of the number of vertices, like it would be a projective plane graph.
Yeah, it might be a dense graph, like not. Yeah, because the graph is constant. So this is a requirement.
If
Yeah,
you understand correctly, eventually you want an infinite family of graphs.
yeah, I want an
So that
infinite family
locally
of
they're
graph.
constant. Like
So that
for every t like that, it will be a
Yes.
constant, but the group.
But if we want to code for infinitely many n's, then we need an infinite family of graph that has this property. Yes. Any more questions about this? Okay, so for our error correcting code, we needed the V1 and V2 to be linear in n, and we needed the degrees to be constant. That is, the sets to have constant size. If you look on the vertices, here is sets. So this is hard to get. And all kind of natural random constructions that you can think of do not have this property. Unlike, if you just take a random bipartite graph, then this would be a sampler with high probability, but this would not work if you want these two layers. If you just takes random sets, like takes S and T just to be random subsets in N, then it is not very likely that any T is going to contain some specific S you have, just because you only take linearly many sets, and probability that they would contain this specific set is not high. So this wouldn't work. If you would take S to be a random subset and T to be a collection of random subsets, then this would also not work, because these random subsets are likely to be disjoint, because they are constant size subsets of n. So they would be disjoint, and then your local graph is going to be disconnected. Yeah. Like not disconnected, like disjoint parts. So it's not going to be an expansion. So this natural construction doesn't work. Another possible construction you might think of, which has good properties, but our algorithm, we need a stronger one to make our algorithm works, is if we take an expander graph and take random walks over this expander to define our sets S and T. So this T is like a random walk of length V2 over H. And then the local graph G restricted to T, so S is like a shorter sub-random walk. And this is not strong enough for us, because if you look on this local graph, so suppose you define if I want this to be a sampler, suppose I defined F here as being 0 here and 1 here, then all sets S either going to see lots of vertices here or going to see lots of vertices on the other side, but they would not see vertices from both sides with like very high probability. So this is also not good enough to make our algorithm work, even though it has good properties in general. So
it's recommended to forget these two slides.
Yes,
Say
they don't
it's a
work.
nice challenge to find other ways of
it's a
getting
challenge.
results.
We tried all kind of random construction with varying kinds of stuff, and the only way we know how to get it is by using high dimensional expanders. So for now, this is actually like, you may think of it as we take like a very simple properties, but we only know that they exist on graphs which are derived from high dimensional expanders. So high dimensional expanders, you can think about them, if you don't know, as like an inclusion graph with sets of every size. And they have many very strong expansion properties. And the only way we could get a graph that has the properties we want is just taking layers out of high dimensional expander.
How high dimensional is high dimensional here?
Like what is
Does it need to be of
it needs to be of constant.
It's too easy enough.
yeah, this is the question basically.
No,
You
because
take it from a higher one.
we need to take like a high dimensional expander with the like, so T, the set V2 is like the maximal dimension that we want. Like T would be the highest dimension in the high dimensional expander, and we can take it to be 2 because we need the graph to be a sampler, so we need a relatively high degree.
Still constant.
Still constant, but like a large constant. If we want a code that has distance which is approaching 1, then it's a large constant. Also, it has to be a large constant. If we look parameter-wise, it has to be a large constant, like if you compare it to the distance parameter. Like if we want distance 1 minus epsilon, then this has to be some double exponential in 1 over epsilon. So dependencies between the constants is not very good. But if all are constant, then this is a constant degree. Yes, so this is the only way we know how to get it, even though this looks like really simple properties comparing to what high-dimensional expanders has, we still don't know how to get there in any other way. So now the main theorem.
You're not going to explain which high-dimensional expanders are you taking?
We don't care. Because, I mean,
What's the cushion? What is your definition? Because high-dimensional expander.
no, so I'm just saying that we know how to get them from high-dimensional expander. I don't want to define what.
Which one you take for?
We only need like really basic properties. We only need what Illutin studied, like did show that these transition graphs are expanders. So
The up-down works.
the up-down works are expanders is all we need. So any construction works. We don't need any
So when you
complicated.
say that you have to take very high dimension, you can get dimension 2 also by taking the prime to go to be bigger, then you get the density as much as you want. You can still do it in just vertices, edges, and triangles.
But we need the sets to be large, like.
Which set?
So the sets here are like D faces of the expander. So we needed this D to be large.
That's okay.
So yeah,
Prime is large.
yeah. So this would be large.
Moreover, you can get even
So it's okay, but it means that D cannot be equal to 2.
what?
D will not be equal to 2. She needs to be 100.
P, the prime can be once you.
No, but the prime, yeah.
The dimension can be 20. That's what I mean.
But I'm not sure.
Wait, is it supposed to be obvious how to get from the expander to the sets? It's not obvious at all. I think.
So what we do, we just take the sets of the expander, of the high-dimensional expander, and then take them to be, no, just take them all.
Yeah, but
Wait, this is too many sets.
Why?
No, all the faces.
All the faces.
Yeah, just the faces.
We just
It's
take
a
the
linear
faces.
number.
but
Okay.
you
You
know,
see,
say
you
what
have all subsets.
We have all subsets, but this is fine. Yeah, this means that actually this constant size graph, like this G restricted to T, are full graphs. But like this, but we don't. This is enough because the number of faces is constant and the size of these graphs is constant. Okay. Okay, so
Wait, so if you just take a random bunch of sets and then all of their subsets.
It will not work.
This will not work,
will not work.
but I mean, I see why it's not gonna work, but
Yes.
maybe like the Lovász-Loka lemma is going to make it work, because like it's true, like every set has
yeah,
some
so
constant probability.
the problem is that we sort of need these. So if you just take random sets in any kind of construction, they would not intersect between themselves enough. Even if you take all their subsets, random sets are not very intersecting.
Basically, I should really mention, because what is hidden here is a fundamental problem in the high-dimensional theory, that we don't know any random construction which really give you strong expansion. Somehow it's, and the question is whether this is a problem of our knowledge, or maybe there is something even deeper. To be honest, I think that there is something deeper, and it's kind of an analog to Margulis type of arithmeticity, which tell you that in Lie groups, you don't have a discrete subgroup when the rank is I, unless they are arithmetic. In some are only the arithmeticity enforced on your existence of some James, and you don't have the deformation spaces. So, but this is a philosophy which I don't know to prove. I even don't know to state it carefully.
We had an argument several times about this. I disagree with Alex, but I let Inbal continue.
I'm just going to comment on that we were hoping that because we required much less than what high-dimensional expanders have, we might still get a random construction. Because this is like, we required only these 3 layers and this local and global sampling, but we still couldn't get it. So maybe even what we required still captures something deep. I don't know. Yeah. But any kind of random thing we tried doesn't work from one rhythm or
It doesn't
another.
have to be random. There may be a combinatorial construction.
Yeah.
You don't need random. You just wonder whether.
Yeah, and any kind of
Yeah.
different construction we tried, whether random or not, did not get these properties. So maybe this is enough to capture whatever is hard to get. Yes.
Also, what I said about local lemma is complete nonsense. It's like definitely deeper than that. Like you can't.
Okay, so our main theorem is that we have a polynomial time algorithm that lets decode the ABNNR encoding if our graph is a part of a double sampler. And what it means is that we're getting some z in sigma to the v1. So each vertex here has some vertex in sigma. And we can find all y's in C prime, which means all y's that are encoding of x here, that when we apply the ABNNR encoding, we get something which is not too far away from our input z. So we could get a distance which is approaching 1 with the parameters. And now I'm going to talk a bit about the algorithm. And in fact, I forget like this last step, and I'm just looking for all x's that if I apply the encoding, the encoding of x is relatively close to z. So I'm going to describe our algorithm in a high level. So as I said, our input here is z, and we want to find x's in the code that when we encode them, we get something which is close to our input. And the first step we do is local lists. So we look on every t, and then on the graph g restricted to t, which is a constant size graph. This is important for it to be constant. And sort of what we're looking here is, so we have some x, like you can think about the one element in the list that we want to get. And here what we're looking for is x restricted to t. So we're looking for candidates of x restricted to t. So this is a constant size string of size, the size of t, sigma here, that when we encode it on this local graph, we get something which is close to our input. So the first step we do is create this local list. This LT is a subset of 0, 1 to the t. That when we encode, we get something close to our input. And in order to get this list, this is the place that we need the local graphs to be samplers. Because we need this list to be bounded. We need this list to have a bounded size. And for that, we need this local graph to be a sampler, else theoretically this list could be exponential in t.
Yeah, this constant is constant relative to the other parameters.
Yes, this constant is not this constant is relative to epsilon and not to t. It's not a function of t. Yeah, this is important because if we had exponentially many strings in t, the next step would not work. So basically here we have a list for every t. And in the next step, we forget everything about this graph and about our inputs, and we only care about the lists. So in the second step, we have a list for every t, and each list contains like a list of different x restricted to t. So we have like some coordinates of x and then a different set of coordinates of x. But like because we have lists and we think about this list as like all of the elements in list are like correct. It's not that we need to throw them out, because we need to do list decoding. We need to output the list of final x's, but we need to figure out how to match them correctly. Like if we have x restricted to this t and x restricted to this t prime, these are like different parts of different x's on different coordinates.
They have to be consistent.
They have to be consistent
on
on
the
the intersection.
intersection.
So the next step we do is for every intersecting t's, we have a matching which forces them to be consistent on the intersection. So sort of we know how to locally match these lists. And this is the second step.
So match, you mean you
Take a list.
edge
Yeah.
between every consistent pair of
Yes.
T and T prime.
Yes, and if we have no consistent pairs, we just put edges randomly. But yeah, or arbitrarily. But yeah, what we care about is that the consistent ones, we want to notice them. We want to match them correctly. Those that are actually part of a global X, we need to figure it out. But this gives us like a lot of small consistencies. And the question is how to take from these small consistencies a single global X. And we do it by getting a constraint graph. So this is a graph which has vertex set V2. So each T is a vertex. And each LT, you can think about it as like the alphabet of this graph. And then each matching is a unique constraint, because between every two lists, we had unique constraints. So we have like a matching for every edge. And
So every L sub T is actually a list.
yes,
So consistency is between elements in this list or
Yes.
elements in the other list.
yes,
So it's not a unique, so it's not a unique thing, but some elements in the list of T may be consistent with some elements. in
yes.
the list.
Okay, this is something I did not mention in the talk, but in the real work, we make sure this doesn't happen. We make these elements in the list far away from each other, so that it's not possible that two different elements are consistent with a single element. And we do have a single, like a unique matching here.
Every pair of elements in each list is 1 minus epsilon prime apart.
Yes. Well, this is a really annoying part, which I didn't talk about because it's really annoying. But what we wanted to
It
happen,
seems to be essential, otherwise.
Yes.
you won't have unique, so
Yes.
that's a property.
it's
of the
essential in the
local-
algorithm.
It's a
Yes.
property of the local sampler, that every
Yes.
pair of elements in the list it generates are far from each other.
Yes, but this is not, sort of this is not strong enough for us, because we wanted that every list element is going to be very far away from each other, but we wanted it to also be close to every sigma that when you encode it is good. So what we had to do was like to choose the R, the how close you are and how far you are from each other dynamically. So we tried some R. If it was good. If not, we increased it, like doubled it, and then tried again. And if it didn't work, we doubled it and tried again, until we reach an R which satisfies these two properties.
So just, you don't know how far they are pairwise from each other in advance. You just know
Yeah.
that they are inconsistent with each other.
Yes,
There could not be a matching between two elements
yes.
on the L sub T and one element in L.
There could. There is always a unique matching. Like even if in the algorithm, it might be that we could not match one sigma to anything in the other list. And in this case that we couldn't match, we just arbitrarily match them in a way that is unique.
But if you can match, there will be only one
Yes.
element here and one
And one element here.
And
That
that,
is consistent, yes,
and nothing else.
and nothing else.
That it seems not trivial to get.
No, it was not. This required like choosing R dynamically, and this means that different T's has different R's. And this means that we had to choose a single R and drop all the T's that had different ones. And this made everything really annoying. but yeah, but I didn't talk about it because I think it's a technical thing and not like the essence of what we're doing. But to get the unique matching, we needed to like dynamically choose how close we are. Like
So then now we can, okay, so it's complicated, but we can think of S sub t as a single sequence.
as a
There's only one element in each S,
no, why only one element?
because you said that the matching is.
The matching is unique. So each element.
Each element here as
As
a
a
single
unique
match.
vector.
Yeah, okay, good. Yeah.
But these like incorporate all the final lists. Like these unique matchings, the good matchings, the ones that are not arbitrary, should incorporate the entire output list. We just need to figure out how to get from these local matchings like a global consistency. And this is like definitely not trivial.
Sorry, what is R in your discussion with Avi?
So we enforced like a minimal distance between the list elements to make sure that we do have unique constraints. And this is the minimal distance that we enforced. So yeah, why doesn't this work? Okay, yes, so we have unique constraints. And what's also good to know is that there is a way to solve unique constraints if the underlying graph is an expander. Not in, I mean, in the general case, this is conjectured to be hard and it's open. But if the underlying graph is an expander, then it is easy. And there is a polynomial time algorithm by our et al. And because we have a sampler graph between the V1 and
That's
V2.
already a paper of Travis on it before.
And actually, we use the paper of Mikhailev and Mikhailev because it has the better parameter for our setting. So we have a unique nth instance, which is on an expander, and it has a high value solution, which is the correct X. And then this algorithm, we use it as a black box. We just run this instance on the algorithm, and this gives us a high value solution.
Yeah, I don't know if everybody knows what the unique games instance is.
Yes.
Yeah.
This is like basically a graph with unique constraints.
The unique constraints means that you can assign alphabet symbols to the vertices, and there is a function telling you which pairs are legal, and this
Is a
function
one-to-one.
is the bijection.
This has to be a one-to-one function to make this the solver works. So the solution just gives us an element for every t, and these elements are now globally consistent. So we can get from them the original x prime, which is close to x, and then retrieve y. So we use this algorithm as a black box, just run through it. And this was our solution. Now,
So the list size will not grow in this process. It will still be, the list size will remain the list size of the
list size will not. The list size would be the list size of the Johnson band, because we can also, we know if X belongs to C, and we know if our encoding is consistent. Yes, so the list size.
Inherited from the local structure, yeah.
So with that, just to make sure I get your discussion with Avi and the Rs, this is what makes it a unique.
Yes, yeah. Okay, so if you think about the algorithm, we don't actually use the fact that X belongs to C until the really last step. So like everything can work if we don't have the promise. The only problem is that this is not even an error correcting code. If we don't have the promise that X belongs to C, if we have here two vertices which differ only on a single vertex, then their encoding is going to differ on a constantly many vertices. So because it's not an error correcting code, clearly it can't really be list decoded or anything. But we can still run our algorithm. And what we would get if we do it is like what we say is an approximate list decoding algorithm. And this means that given an input, we can find an approximation to every X that when we encode it, it is close to Z. This is the also, you can get it from the majority decoding with half here. Because also there, the fact that X belongs to C, you only get it, you only use it in the last step. Like the algorithm doesn't actually care about X. So this was about the algorithm. Are there any questions about it? So I'm going to talk a little bit about more recent works. So we did the first list decoding algorithm for the ABNNR encoding. There is work by Levital and also by Geronimo here that list decode the direct sum encoding, which is the error correcting code in which instead of each vertex collects the bits of all its neighbors, then they do a XOR of all its neighbors. So it's a more efficient error correcting code. And they also did it on a larger class of graphs, not only on graphs which are from high-dimensional expanders, but also on graphs which are derived from random walks over an expander graph, like the example I said that did not work in our case. So it did work in their work. And there is some similarity in algorithm, like in the idea that we use the unique game solver, which itself uses semi-definite programming along the way. And in their work, they use some square semi-definite programming directly in their algorithm to get it. There is also even later work by Geronimo et al. That they found a polynomial time decoding algorithm, not list decoding, for the error correcting code of Tashma, which has like it has nearly optimal rate distance trade-off, and it was not known to be efficiently decoded before. So this was a question that was open, and they managed to decode it efficiently. And there is some connection in the underlying structure, which I don't know, maybe I think it's interesting that in all these works, so in their work, they define a property they call splittability, which also sort of speaks about expansion on sets of different sizes. This property you can get from random walks over an expander graph, so it's better in this respect. But I still think that there is some connection in this decoding algorithm that they require these like properties that the graphs connecting sets of different sizes of different levels should be expanding. So I find it interesting. And this is it. Thank you.
Questions?
What is known about if you want to limit the alphabet to even not binary, but something that does not depend on the
parameters?
So she's mentioned the result where you can get binary code by Fernando's result.
You can get binary code if you do the direct sum encoding. In our world, the alphabet size is connected to the distance, more or less. Like there is just a trade-off between the alphabet size and the distance you get. So if you want small alphabet, you would get like a smaller distance.
Okay.
Yeah, but you can get binary if you do the direct sampling.
I still think double samplers are inherently interesting because
I'm not sure. I mean, when we finished this work, I thought, and then we tried to get a construction in a lot of different ways. And now I think, I don't know if I agree with Alex about, I mean, I don't know anything about what he said about the being inherent difficulty, but I think we might have hit some obstacle, which currently it seems like the only way to get it is by high dimensional expanders. So I would think that they would be interesting by themselves if there was a different construction which get them.
maybe like in the single samplers, right, that they're connected to extractors and expanders and PRGs, because they're overall equivalences connections. Is there any connection with the double sampler case other than HDX gives a double sample?
I don't know of any.
It's very different than the extractor game. They want constant degree. There's no logarithmic degree here. So it's,
Yes.
it it's really more on the expanded side than the extractor side.
So I'm still wondering if this inherent difficulty getting high-dimensional expanders when the number of hyper edges is linear in the number of vertices, it seems like, I don't know, can you explain again if I just take an expander and then I take all the, I don't know, 5 neighborhoods of every vertex?
Why wouldn't it work?
Why wouldn't it work?
Okay, so the problem is that most of your vertices, if you take the 5 neighborhoods, most of your vertices are like at the boundary.
On an expander.
Even on an expander, unless
No,
it's
but
like.
it's a constant degree. So what is most here? It's
No,
a constant.
yeah, it's constant, but okay, a large fraction of your neighborhood is at the edge, and
Yeah.
then they're only connected by your path to the center, more or less.
Yeah, but is this a big,
Well,
so
let
you'll
me-
get a worse constant, but you
No, it's really important what the expansion, what the local expansion is. It's here the challenge that I guess our disagreement is Alex. It may have a combinatorial solution. You just design a graph of constant degree. Let's call it D. Okay, so that the induced subgraph on the links on every neighborhood of the vertex is a really good expander. So it's a D, it's a graph on D vertices, and in this induced subgraph, you want the second eigenvalue to be less than a half.
Yeah.
Less than a half.
Then you can.
If you want a half, you can get even a planar graph to it. Okay, you want it less than a half, so really good expander. This is, nobody knows how to do this.
But this is for the other applications. For here,
No, but
it seems to be-
Here is
we need
also, they don't
Yeah,
need it.
we need.
They need something better even, yeah,
I think,
Okay.
they need a
No, maybe-
second eigenvalue close to 0 as a function
Yeah.
of D, like they need D to the epsilon or something.
we need something which goes to 0, yeah.
It's not,
What was the problem you just said? Can you repeat it
you
slowly?
know,
I knew.
design a graph, it's a family of graphs, but of constant degree D, so that every link, the induced neighborhood of every vertex is an expander of second eigenvalue below a half.
Less than half.
Yeah.
No, now I see. You don't want it to go to 0 with D. Yeah, okay.
She wants to.
I mean, I want the second, I
She
want
wants it to go to 0 with D.
Second
It's like D
eigenvalue.
to the epsilon.
like, I want this local graph to be.
The 0.9. But less than half is still unknown. Okay.
Yeah.
Less than 0, yeah.
Yeah, I mean, this, if you want to do it in neighborhood, maybe there is a different way, but also different ways you can do it.
Without high
I'm also
dimensional.
confused.
Without high-dimensional expander. Because from high-dimensional expander, get it.
That's what they use. I was asking, that's all about doing it differently. Yeah, these things you can see, maybe you can do it differently. Who knows?
You want to take me,
Yeah, so things
you
that.
want to take me with the only little advantage I have from the other.
Isn't it enough to?
I did it once, why should I try again?
You confuse me. Isn't it enough to just get a Chigger constant that does not go to, that stays bounded away from 0?
No, it should be above a half. If you scale it so it's between 0 and 1, if you want the Chigger constant, if you want the, it should be over, it should be close to 1.
For your application.
For this application, yeah.
I missed this.
Yeah. No, it's not obvious from the presentation, but you need it, yeah.
Okay, but if I just want, to
for-
be bounded away from 0, then I can do what I.
Yeah, but then, yeah.
Okay.
Yeah. But then you can even have planar graphs. There will not be global expanders, but locally you can have.
Yeah.
You can take the triangular lattice.
Yeah, but I need them to be a global expander also for the.
Yeah. More questions? All right, thanks.